In the last session, we have started our discussion on type A amplifiers. In this session, let's find out some important parameters of class A amplifier. Let's start with the voltage gain. We know that the voltage gain of an amplifier is defined as the ratio of AC output voltage to the AC input voltage, that is VO by Vin, where VO is the AC output voltage and Vin is the AC input voltage. And we have already derived an equation for this voltage gain in common emitter configuration. And since type A amplifier is a common emitter amplifier, the formula holds good here, which is RL by RE prime, where RL is the AC load resistance or the resistance that is seen by the AC signal at the output. And this is given by the parallel combination of RC and RL, where RC is the collector resistance and RL is the load resistance. If RL is absent, then we can say that this is equal to RC. And RE prime is the AC emitter diode resistance, or this is the resistance which is seen by the AC input signal in the base emitter region. So this is the first parameter, the voltage gain. Now how do you find out RE prime? RE prime can be calculated using the transconductance curve. We know that the transconductance curve is the curve drawn between the input voltage VBE and the output current IC. When you draw the transconductance curve, it will be like this, and we take a slope, and the slope is delta IC by delta VBE, and the reciprocal of this slope, delta VBE by delta IC, will give you the RE prime or the AC emitter diode resistance. So finding RE prime and RL, we can calculate the voltage gain of a type A amplifier. Then comes the next parameter, the current gain or AI. Current gain is the ratio of the output AC component of current to the input AC component of current, and that is given by IC by IB, which is nothing but beta. Finally, we have a power gain or AP. To find out the power gain, we need to find the AC input power and the AC output power. The AC input power is given by Vin into IB, where Vin is the AC input voltage and IB is the input current. And the output power is minus VO into IC, where VO is the AC component of the output voltage and IC is the AC output current. So applying these two equations, we will find AP as minus VO into IC by Vin into IB, but VO by Vin is AV, the voltage gain, and IC by IB is the current gain, AI. So we get it as minus AV into AI. The minus sign refers to the fact that the output signal is reversed in phase, the phase reversal of the output signal. Or we can write it as AV into AI or minus RL by RE prime into beta. So this is the power gain of a type A amplifier. Now we shall see the efficiency of a class A amplifier. Before discussing the efficiency of a class A amplifier, we need to understand what is happening in the amplification process. By definition, an amplifier amplifies a weak AC signal into a large AC signal. This definition is sometimes misleading, as though the transistor is some magic box which magnifies the AC signal by itself. In fact, a large DC input which is given to the transistor is modified in accordance with the small AC signal which is given. So the output AC is in fact a modified form of the DC input signal which is applied to the transistor through the biasing circuits. So this is what is actually happening in the amplification process. When no AC signal is applied to a transistor, the condition is called a zero signal condition. At the zero signal condition, the average DC power supplied to the circuit could be written as P in DC. This average DC power is expended in two ways. One, a portion of the power is dissipated in the load resistor itself. We can write it as PRL DC, where RL is the load resistor. PRL denotes the power dissipated across the load resistor, and it is DC. And this is given by ICQ square RL, where ICQ is the quiescent point current. This is the quiescent point current, or we can call it the zero signal current, into RL, where RL is the load resistor. Let's put that as equation A. Another portion of this DC input power is dissipated in the transistor itself. We represented it by P transistor DC or PTR DC, which is equal to VCEQ into ICQ, where VCEQ is the voltage across the transistor, or the voltage across the collector emitter region of the transistor. This is equation B. Now, what happens when an AC signal is applied at the input? When the AC signal is applied, the quiescent point shifts up and down. The output current will increase and decrease from this Q value. It may go up or go down. The collector emitter voltage, that is VCE, also increases and decreases. It is to be noted that the signal variation are limited to the linear region of this load line. This is the load line. So the average value of collector current is ICQ itself, and the average value of the collector emitter voltage is VCEQ itself, because the operation always takes place within the linear region of this load line. Now, the total average power supplied to the circuit by the collector supply. The collector supply is VCC. It is given by P in DC, and P in DC is VCC into ICQ, where VCC is the input DC voltage and ICQ is the quiescent point current. We know that VCC is nothing but 2 times VCEQ. VCC is the maximum voltage that is possible. That is the input DC voltage, and that is double the value of the quiescent point voltage. So we may write it as 2 VCEQ into ICQ. Put this as equation 1. The power consumed by the load resistor is ICQ square RL. We have already written that as equation 1. Then what remains is the power which is dissipated in the transistor. Clearly, the power dissipated across the transistor will be the difference between the supplied power P in DC and the power which is dissipated across the load resistor PRL DC. So P transistor DC is P in DC minus PRL DC. That is equation 3. The power consumed by this load resistor is dissipated as heat. The DC power which is supplied to the transistor is utilized in 2 ways. The first one is the AC power across the load resistor RL. So a portion of the transistor power is utilized in creating an AC power across the load resistor, and this is taken as our AC output. So this is POAC equal to I square RL, where I is the RMS value of the AC output current, which is V square by RL, and V is the RMS value of the AC voltage, which could be further modified as V0 square by 2 RL, where VO is the peak value of the output voltage and VO is the peak voltage. The peak voltage is nothing but VCEQ. You cannot get a value which is greater than VCEQ because the transistor is operating in the linear region of the load line. So we may write it as VOIO by 2 Or again we can write it as VCEQ ICQ by 2. This is equation 4. Why I0 came here? Because I0 is V0 by RL. So modifying V0 square by 2 RL, we get V0 I0 by 2. Now, another portion of this transistor power is utilized in generating heat in the collector region. This is dissipated as heat, or this is the lost power, and we represent that by PC DC. So the input DC could be written as the power across the load resistor and the power expended in the transistor. And PRL DC is ICQ square RL from equation 2 plus P transistor DC, which has two parts. First part is the AC power generated across the load resistor, which is I square RL from here, and then the power which is dissipated in the collector region, which is PC DC. Put this as equation 5. So these are our relevant equations. Using these equations, we need to find the overall efficiency of the amplifier. The overall efficiency is represented by eta 0, and eta 0 is defined as the ratio of the average AC output power to the average DC input power, or POAC by P in DC. POAC, as we know, it is V0 I0 by 2, where V0 and I0 are the peak voltage and current at the output, divided by P in DC is the average input power supplied by the DC supply to the circuit, that is VCC into ICQ. Modifying this equation, we already know that V0 is nothing but VCEQ and I0 is ICQ. So you can write it as VCEQ into ICQ by 2 divided by VCC is 2 VCEQ from the AC load line. We know that ICQ is here. So cancelling Q, VCQ, VCEQ, VCEQ, ICQ and ICQ, we get 1 by 4 or 0.25, which means the overall efficiency of the class A amplifier is 0.25, or this corresponds to 25% efficiency. The maximum possible overall efficiency of a class A amplifier is only 25%. Finally, we need to calculate another efficiency, the collector efficiency. The collector efficiency is defined as the ratio of the average AC output power to the average DC input power to the transistor. We know the value of average AC output power, VCEQ into ICQ by 2. And average DC input power to the transistor, it is not the total power supplied by the power supply, but it is a power which is dissipated, which is generated, which is available to the transistor only. And that is VCEQ into ICQ. VCEQ is the voltage and ICQ is the corresponding current. So cancelling VCEQ and ICQ, we get it as 1 by 2, or this corresponds to an efficiency of 50%, or the collector efficiency of a class A amplifier is 50% maximum.